But as far as the quiz for this week goes, quiz 2, it'll be over sections 1.1 and 1.2. So we'll look at the homework for those. I posted the lectures. I'll show you where those are. Sometimes I like to take examples out of lectures, so if you have your notes, review that. But just get prepared. Okay. Before I start, let me show you quickly. Hopefully you got my email. If you didn't, then I will show you. On my website, I created a new link called Math 181 Study Aids, which doesn't have much on it, but eventually it'll have a review sheet. I'll get that up next week probably. Right now it has all the lectures that I've recorded so far. If you want to watch the ones for 1.2, they're right here. I don't know how great they'll help you, but they're there. And I will just fill these in as we go along. It also has the homework assignments, so you can go to this page to get the homework assignments, or unless you have them printed out already. But anyway, that's what I did on Friday. Well, for this class, I want anything else I was supposed to ask? You know what your quiz is on? You know where the lectures are? All right, questions for me? How'd the homework go? Look at 1.2 yet? What do you want me to answer? 25, 27, 28. What? 25, 27, 28. 1.2. Let me look. Is that the epsilon delta stuff? Okay. As far as I'll just go through. Let's start with 25, and then we'll just keep going until we run out of time and need to start new stuff. Okay? So number 25 from section 1.2. Let's see. It gives you limits of piecewise function. So it wants you to identify the values of c for which the limit exists. Oh, I see, okay. So it gives you this function f of x equals, and then it gives you x squared, 8 minus 2x is 4. And it gives you some domain restrictions, x less than or equal to 2, x between 2 and 4, and I assume x greater than or equal to 4. And we're supposed to sketch the graph and then identify where the limit exists. So let's start by sketching the graph. How would you graph something like this?
Parabola with the left side, and then on the right side go to 4.
Yeah, so you have to graph it in pieces because it's a piecewise function. If you start with the top piece, this is like y equals x squared for all the x values less than 2. So let me go ahead and make my Frankenstein graph here. Probably, since we break it 2, make it more like this. So let's see, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. We break it 2. So less than or equal to 2, we're going to have y equals x squared. Between 2 and 4, we're going to have y equals 8 minus 2x. And then after 4, we're going to have y equals 4. So what's very important when you're graphing this is what happens at these breaking points. So let's start with x squared. You all know x squared looks like a parabola, hopefully, a u. So it's going to go up over here. Now, where is it going to hit this breaking point here? The y value is going to be 4. Does that make sense? Now, is it going to be an open circle or a closed circle, and how do you know?
Closed.
Closed because it's equal to, right? So I'm going to make a closed circle, and this is going to specifically be the point 2, 4. What does 8 minus 2x look like? It's a line, right? So you can just plug in a couple of points to get a line. Specifically, you need to know what happens at these boundary points, these breaking points here. So I would go ahead and plug in 2 and 4, even though they're not part of the line, right? I would plug them in to figure out where the line is going to start here and where it's going to end here. So let's do a little chart on that.
2 and 4 for the first one.
X, Y. So for this line, I want to know 2 and 4. When I plug in 2, I get out 4. How nice. And when I plug in 4, I get out 0. So this guy happens, he would be an open circle here. Because he hits the same point as this guy hits. But it's kind of stupid, by kind of stupid I mean incredibly stupid, to draw an open circle over a filled in dot. Okay, the filled in dot always wins. Alright? So it can't be open if there's a solid dot there. So this guy starts at 2, 4, done, goes to 4, 0, like this. Right, and then finally for x greater than or equal to 4, you have a horizontal line because it's just the graph y equals 4. It's going to have a closed circle on the breaking point here because this is an equal to. So there's your graph.
There's the limit.
So yeah, so the question, the second part of the question is, where doesn't the limit exist? That's the only problem. Everywhere else, any other x value you pick, there's no jump, right? There's no, from the left and the right, you'll be approaching the same thing. And no matter which x value you pick, the left and right are approaching the same thing. But at 4, there's a problem. The limit doesn't exist. Ooh, I like 27. Quick questions about this though. Yes?
I got lost a little bit on the
Okay.
4,0. Why is it 4, 0?
So I realize this guy's a line. And to graph a line, you just need 2 points. So I picked these two x values as my 2 points. So I took 4 and plugged it in.
Okay.
And when I get 2 times 4, that's 8. So 8 minus 8 is 0.
Okay. See.
Anything else about this guy?
Can we do 32?
32? Yeah. Yeah, we can do 32. But let's do 27 first. Let's do 27 first. So number 27, sketching a graph. So they give you some conditions that a function is supposed to satisfy, and then you have to come up with a graph that meets those conditions. So it gives you, let's see, f of 0 is undefined. The limit of f of x as x goes to 0 equals 4. So I'm going to write these down. Here's your conditions. F of 0, undefined. Limit as x goes to 0 of f of x. 4, I think. F of 2 equals 6. And then the limit as x goes to 2 of f of x equals 3. So they're giving us a bunch of different conditions, and we have to graph a function that satisfies these conditions. So what do you think? Let's focus on these first two conditions. How can f of 0 be undefined? How can a function have an undefined value at 0?
0 on the bottom?
So again, I don't think it's asking us to come up with an equation. Actually, sketch a graph. So we want to come up with a graph. So on a graph, you can either, in order to be undefined, you can either have a vertical asymptote or a hole. Those are kind of our only two ways that we end up being undefined. So do you think this is going to be a vertical asymptote or a hole, and why? A hole. Right, a vertical asymptote is not going to have a limit. So f of 0 undefined has to be a hole because my graph still has to approach 4. If f of 0 were undefined because of a vertical asymptote, it couldn't approach 4 there. What about f of 2 equals 6 and then a limit as x goes to 2 of f of x equals 3?
Piecewise.
Say it again?
It's a piecewise graph.
Yeah, well, you would have to use a piecewise equation to write it, but as far as what happens on the graph,
So we
It's
can
like a
find
line
our
and it goes
slope
to
that
3,
way.
but the point's at 6.
whether it looks like a line or not, we don't know, but yeah, it's approaching the y value of 3, okay, but then it jumps up to 6 as soon as you get to 2. Right, so as x approaches 2, we're going to approach y equals 3. That's what this means, approach y equals 3 from the left and right. But then this guy means exactly at 2, we're going to have to put a point.
2, 6.
At 2, 6, when x is 2, y is 6. And in between there, you can do whatever you want, really. Right? Because they don't give you enough conditions to make the graph, to pin the graph down specifically to one function. So really, we just have to make sure that these two things work out. So f of 0 has a hole. So whatever my graph does over here, don't care, doesn't matter, doesn't matter, doesn't matter. But as soon as it gets to the y-axis, it has to have a hole because f of 0 is undefined. And more importantly, there's a y value that it has to approach. So this y value here has to be 4. And it has to be approaching this on the other side too. So now the limit of your function as x goes to 0 is 4, because as x gets closer and closer to 0, the function's approaching the y value of 4. But f of 0 is undefined because there's a hole. So we've taken care of this one. And then as x goes to 2, we have to get up to 6. Well, there has to be a point at 2, 6. But actually, our function approaches 3. So what I want to approach here, 1, 2, 3. 1, 2, 3. This is the point I want to approach. But it won't actually be, this is saying when x is approaching 2, y is approaching 3. So when x is approaching 2, y is approaching 3. And this is good, this takes care of this. But I left a hole there because then I need to jump up and go to 2, 6 for my actual point. Got a gaping hole. So we're approaching, as x goes to 2, we're approaching the y value of 3 like we're supposed to, but actually at 2, the function's up at 6. This stuff in between where I decide to go up and down, it doesn't matter. You can put whatever you want in between because there's no condition except at x equals 0 and x equals 2. Bueno or no bueno? How, suppose in this first instance here, I said I wanted f of 0 to be undefined, but I also wanted the limit as x goes to 0 of f of x to be undefined. Suppose I change this. What does that change about my analysis here?
Being vertical asymptote hole.
One way to do it would be to put a vertical asymptote here. Right? If you put a vertical asymptote at x equals 0, then both of these will be undefined. Is there another way to do it?
Jump.
A jump. But you'd have to put a hole on both ends of your jump. So for, let me go over here real quick. If I just gave you the condition that f of 0 is undefined, and limit as x goes to 0 is also undefined. There's a lot of ways to do this, but two popular ways might be vertical asymptote here. This guy works. Certainly f of 0 is undefined because you never reach the vertical asymptote, and the limit's also undefined because you're going in different directions, so you're never going to approach a single y value. Another way to do it might be maybe you put a hole here in a straight line, and then a hole here in a straight line. It has to be a hole on both of these because f of 0 is undefined. If you fill in one of these points, f of 0 wouldn't be undefined. The limit's undefined here because you're approaching two different y values. You know, whatever this is some positive y value, this is a negative y value. They're not converging from one y.
Is that still correct even though you don't have the 4? You can just put any number, like, right, if we put a hole at 4.
Well, yeah, that's because of this.
Right.
But I changed
Since they're
that.
both undefined. then
Yeah.
just put it
Anywhere you want, as long as they don't meet up. Yes, sir.
This is oscillating, there's no limit. How would that, how would that be true?
So
I forget the,
no, it's okay. There's a function. Here's a function. So another type of problem you might occur that might occur so that you don't have a limit is an oscillation, infinite oscillation situation. So you can think of something like y equals sine of 1 over x. If you want to calculate this limit as x approaches 0, what's going to happen with this graph looks, well, here, let me graph this for you. Sine of 1 over x. Oh no, there we go. So this is sine of 1 over x. And as you zoom in on 0, see what's happening? It's just super oscillating. It's just going up and down as much as it possibly can. So, over here it's not oscillating so much. But then as it gets closer and closer to 0, it starts going back and forth, and it never actually reaches anything. It never actually converges. So the limit here would not exist.
Is that finite, or is that just go on forever? I mean, there's gotta be a point in there somewhere where
Well, when you plug in 0 for x, what do you get? I'm fine, right? So first of all, there is no actual point, right? It doesn't actually ever get to here. This guy's
Maybe like a hole.
So it never crosses.
No, it never actually touches the y-axis. So think of, so we're focusing on the limit. Oh, I shouldn't put the any there. I should put the limit as x goes to 0 doesn't exist. Other limits do, but as x goes to 0, sine of 1 over x has a problem. So what's happening is, as you plug in things that are closer and closer to 0, so like a fraction that's close to 0, like 1/10, you'll get actually sine of 10 because you have to flip up the 1/10. right? And then sine of 10 is some number. But if you put in 1/20th, you get sine of 20, which is some other number. And then sine of 30, sine of 40. And so it's because sine oscillates, as your numbers get smaller and smaller, this just keeps oscillating. It doesn't ever converge on anything. It's a crazy function. Very crazy. This is equivalent to thinking of what happens to the limit as t. We haven't talked about infinite limits yet, but this is equivalent to this. Instead of going to 0 with 1 over x, you can go to infinity with t. So what I'm saying is if you replace this one, if you replace 1 over x with t, well, if 1 over x is going to 0, then t must be going to infinity if these are equal. So if it makes more sense, think about what happens to sine as you go to infinity. Do you guys know what happens to sine as you go to infinity? It's oscillating. Forever, it just goes forever. It never stops. It's never going to converge on a single y value. So this guy, the fact that way out in infinity, this guy doesn't converge to any single y value is equivalent to this guy at 0 not converging to any single y value. So this is a crazy function. Did that answer your question?
Yeah, I was thinking what someone else said with the whole, like it would eventually, start converging on the whole. Like it's some infinitely small number.
Well, think about it like this. What's sine of 1 over, one over 2 over 3,000 pi. This is a small number on the bottom, right? This number's close to 0. Close to 0. So if you take 2 and you divide it by what, 9,000-ish, it's going to be very close to 0. But what does this evaluate to? Well, it would flip up, right?
1,500 pi.
So it would be 3,000 pi over 2, which is 1,500 pi. So then that's equal to, what's sine of 1,500 pi? What's sine of 1 pi? Or 2 pi, I guess. Okay, but now, take something a little bit smaller, a little bit closer to 0. Plug in 2 over 3,001 pi. So I've made this denominator bigger. So this fraction is even closer to 0. Now when you flip it up, you get sine of 3,001 pi over 2. This guy should be...
Would be, what was it, 1/2?
1. Right, because this is a pi over 2 reference angle. Right, 3,000 pi over 2, that ended up being 1,500 pi. So for this guy, you landed here. 1,500 pi lands here. Right, 2 pi, 4 pi, 6 pi. If you keep going, this will be 1,500 pi in the unit circle. But this guy will go 1,500 pi, but then he'll have 1 pi over 2 left over. So here's 1,500 pi, but then this guy lands up here. So this is 3,001. So it goes 0, then it goes 1. And then if you put 3,002 pi, then it'll be back to 0. If you put 3,003 pi, it'll be at -1. If you put 3,004 pi, it'll go back to 0. So it just keeps oscillating as you get, every time you increase this guy by 1 unit, it's getting smaller. The x value is getting smaller in the bottom. So it never actually converges on you. the calculator's freaking out trying to graph that. Doesn't even know what's going on. All right, so the other one I heard was 32. But questions before I erase this? So 32 is trying to get at something called the epsilon delta definition of a limit. So let me talk about that briefly. The epsilon delta definition of a limit is the formal definition of a limit. That's the thing that, when mathematicians prove things, they use that definition. I kind of want you to understand it, but I don't ever actually want you to I'm never going to make you use it, but I would like you to understand it. So let me write it off over here for a second. So, talking about this value, the limit as x, given epsilon greater than 0. So if you give me some number greater than 0, okay, but close to 0, the intention with this is a variable, but the intention is that it should be a number that's close to 0, but not equal to 0. Given epsilon greater than 0, the statement, the limit as x goes to c of f of x equals L, right? Saying the limit equals some L is equivalent to saying there exists a delta greater than 0 such that if the absolute value of x minus c is less than delta, actually bigger than 0, then the absolute value of f of x minus L is less than epsilon. So this is the technical math definition of a limit. This is trying to get at the idea of what do you mean by arbitrarily close to L, and what do you mean by approaching C. So before I get to 32, let me give you a slightly simpler example. Okay? So consider the function f of x equals 3x minus 5. So this shouldn't mean anything to you, maybe it would never mean anything to you, but consider this function for a second. What would you tell me if I asked you the limit as x goes to 2 of f of x?
1.
1, right? Because we know this is a line, and as x approaches 2, we can plug it in and get 1 out. So, because that limit equals 1, or because we think that limit equals 1, if I give you an epsilon, then you should be able to find a delta that will make the function within epsilon of the limit. Now that doesn't mean anything, so let me try to make sure. This guy is what? A line with slope 3 going through negative 5? 1, 2, 3, 4, 5. Slope 3. So he goes up 3, 1, 2, 3, 4, 5. So he goes up 3 over 1. Up 3 over 1. Etc. So this is my line. I want to blow up, for my purposes, I want to zoom in on this particular area here. So let's see, 1, 2, 3, 1. I know I go through 2, 1. And then I have a line going like this. Something. So this is my guy 1. This is my guy 2. So what I'm saying is give me an epsilon. So give me a small number that's close to 0. Pick it.
0.09.
0.09, that's what you want? Alright.
It's a number.
It's fine. It's fine. 0.1, that'd be too easy. 0.09. So what this definition is saying is that I can find you an x value around, I can find you a sort of width around the c value of 2 because c equals 2 in this particular instance. I can find you a width around this c equals 2 so that my function stays within 0.09 of the limit 1. So I'm using green actually. So this guy up here is going to be 1.0. Let's not do that. I think I like too hard. Let epsilon equal 0.1, okay? I'll round up for you. So I want to be able to stay within 0.1. So above, if I go 0.1 above, I get to 1.1. And if I go 0.1 below, I get to 0.9. What I'm saying is I can find corresponding x values down here so that as long as my function is between those two x values, my function so as long as my as long as my domain is between those two x values, my y values will be between these two y values. So over here where it says absolute value of f of x minus L is less than epsilon, you should interpret this. Let me use the 0.1 for a second. F of x minus our limit, which is actually equal to 1, absolute value should be less than 0.1. This is what we want. Do you remember how absolute value inequalities work? How do you solve an absolute value inequality?
Put a minus and put a 0.
Yeah, you put a minus on one side, a plus on the other side. Right? So what this means is x minus L has to be between 0.1 or negative 0.1. Remember that? And L was 1, so I should be writing 1 here instead. And if you add 1 to all sides, what do you see? Well, this is going to be 0.9. Should be less than f of x. Should be less than 1. So this garbage here, f of x minus L absolute value less than epsilon, is trying to say if you give me an epsilon, then I want my y values to stay within a tolerance of epsilon. That's what this is trying to say. And this part is trying to say that there exists a delta, a tolerance on the x-axis that will make that true. So in this particular case, how do you figure out this tolerance here? How do you figure out how far you can go from 2 before you're outside of this green range?
Replace that value in x in the actual function.
Yeah, this is a y value. So set your function equal to 1.1 and see what the corresponding x value is. So one way to figure out what this point is, because this point is going to tell me how far I can go on the right, and this point is going to tell me how far I can go on the left. So to find these x values, you can say, let me set f of x equal to 1.1. And here you can set f of x equal to 0.9.
Like 2.3 on one side.
Yeah, so you have to solve 3x minus 5 equals 1.1. So 3x equals 6.1. So you divide both sides by 3. Equals
2.333.
2.3-ish. That's not right. 2.03?
2.03, sorry.
That's close. What about here, when you set it equal to 0.9, 3x minus 5 equals 0.9, add the 5, 3x equals 5.9, divide by 3.
1.3 something?
So now it should be closer to 1.97 or
Minus.
something. So what's your delta? What's your tolerance here? How far can you go? Right? How far are each of these x values away from 2?
0.03.
0.03. Right? 2 is somewhere in the middle. If you go plus 0.03, you get here, and if you go minus 0.03. I'm sorry, 0.3. So if I said find the delta that satisfies the definition of the limit for epsilon equal to 0.1, you would tell me delta equals 0.2. As long as you're within that tolerance, your y values will be within the correct tolerance. And the reason that this characterizes what you mean by arbitrarily close, because what I'm saying is, as soon as you tell me this limit equals 1, then no matter which epsilon you give me, I can find you a delta so that my function stays within epsilon. So like if you gave me epsilon equals 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 I can come over here and find you a region on the x-axis that will ensure my y values stay in that small region.
Is it gonna follow the slope then?
For lines,
I mean, so let's say you do 0.1. Well, the slope of the line is 3, so you're just gonna adjust it.
yes, for lines. For lines. It generalizes to functions that aren't lines, though, so you have to be careful. So let me do 32 then, and then maybe we'll move on. So they give you in 32, find out if we get epsilon graph. So they give you f of x equals x squared minus 1. They actually, looks like they gave you a graph, but I can put up a graph right here. Find delta such that if 0 is less than x minus 2 is less than delta, then f of x minus 3 is less than, okay, so let me draw a graph first. So what's x squared minus 1 look like? Parabola, right? But shifted down 1. And we're interested in eventually the limit as x goes to 2. So this guy's going to look something like, these are all 1, 2, 1, 2, 3. So, saying find delta such that zero less than absolute value of x minus 2 less than delta. So if this is true, then the absolute value of f of x minus 3 is less than which they want to be 0.2. So you want to think of these as tolerance statements. Right? This is saying find a tolerance on the x-axis, find how far you can go away from 2, so that f of x doesn't go more than 0.2 from 3. So this is the projected limit. And this is your y value tolerance. This is your c value up here. This is what your x's are approaching. And this is your x value tolerance. So on my graph, I'm going to have tolerance of 0.2. So I can go 0.2 in either direction. And then I need to figure out what that corresponds to down here. So what am I going to solve? Because I have, let's see, what are my, okay, let me go back a minute. What are my y values then? How high do I get up to here?
0.2.
3.2 altogether, right? And how low do I go down here?
3.2.
2.8. So I know these y values I want to stay between, and I have to figure out the x values that'll work. So I'm going to have to solve what equations?
If the x equals 3.2 and if the x equals 2.
So I have to solve f of x equals 3.2, and I also have to solve f of x equals 2.8. Once I know that, then I'll be able to figure out what my tolerance is on the x-axis. But I know what f of x is. It was given to me. So x squared minus 1 should equal 3.2. X squared equals 4.2. Square root both sides. X equals plus or minus root 4.2, although the minus is stupid because we're not over here. Square root of 4.2. So 2.0493. So this x value down on the right here let's just round it to 2. So this x value down here is 2.05. And then to get the other one, I have to solve this equation. So plug in f of x, add 1 to both sides, square root. Again, the negative response, the negative solution is not useful because I don't care about the left side of my graph. Now I just figure out the square root of 3.8. Oops, not 43.8. Here it's 1.95. So what should delta equal?
0.05.
So if you pick a delta equal to 0.05, your function will stay within a tolerance of 0.2. It happened to turn out that these are the same. They don't have to. So for example, what if I would have gotten, because of my rounding they ended up being the same, but what if I would have gotten 1.98 here? What would delta have to be?
0.02.
Yeah, if you get 1.98 here, you can't take delta equal to 0.05 anymore. Because if you go 0.05 over here, you're going to be outside of that minimum value. So you have to take the smaller of the two always. So in this case, it would be 0.02. That's not what happens, right? We got this.
So you're saying if I end up out of rounding up with 2 different numbers, I always use the smallest.
Use the smaller distance, yeah. Yeah, you want to make the smallest interval possible out of those two.
Thank you.
Okay, so this is a fairly complicated idea. All right, I probably won't put a quiz question on this. Extra credit on a test, maybe. Who knows? But I would focus definitely on problems more like the ones we did before this. But still, it's there. I assigned it, so we explain it.